Right, this is Skills Homework 6. If you're watching this video, you really are a glutton for punishment. You're going to watch me draw 3 graphs. Mites and columbolons, okay, on a area of grassland, and means were recorded over a year. Plot the results. Okay. So we have got an x-axis and a y-axis. On the x it's going to be what we specify, so we are choosing the months, and on the y it's going to be our dependent variable. So x is the independent variable, so independent variable there, and the y here is going to be our dependent variable. And we've got 2 dependent variables, the mites and the columbolons. Not Colombians, they don't live in Colombia, they live in grassland somewhere. We need to look at our scales and see what fits on. We have got some graph paper that's pretty tricky to use. The bottom one's okay. How many months do we have? We've got December, January. We've missed out February, but we need that on our scale. March, April, May, June, July, August, September. So we need 10 things. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we are. So we could start this off with December, January, February, March, April, May, June, July, August, September. We need a figure at the origin as well, so that would have to be the one before November. So that scale's fine, or you could have moved the entire thing one there. But we need a linear scale here. We can't miss things out, or else it's going to make our graph look distorted. So those are our x-axis points for our independent variable. And going up on the y, our dependent variable, we look for the biggest number that we've got. So the biggest number is 298.3, it's going to be 300. And so, right, if you can see how these go up like that, and then it's just a case of trial and error which ones we're going to use. So we could go, do we go up in hundreds, tens, 20s, 40s? More or less. Okay, so if we go up in tens, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and that's about a third there. So that's going to, 200 is going to be there, 300, that's going to fit on. So this scale we can put on, so 10, but we're going to have a number at the origin as well, so we're going to have 0 there, and so on. 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 200, 210, 220, 230, 240, 250, 260, 270, 280, 290, 300. Suspiciously perfect scale that they've given us. If we'd have gone up in 20s, we'd have used exactly half of the available paper, and the rule is that we need to use more than half, so that scale wouldn't have been any good. And I'm going to draw our axes lines. Some students have not drawn these, but they do need to be on. Okay, so there's our axes. We've got the values on our axis, we just need to label our axes. When you were labelling these, we need to put on what we've got on the in the table. So this is going to be month at the bottom. So it doesn't matter where we put these, as long as it's near the axis somewhere. And we have got, it just says mites and columbulands, but what were they? It says the mean number of, so that's what I'm going to put. But is it mites or columbulands? If I just put organisms, then that'll cover us there. So mean number of organisms. Okay, and now we just need to plot. So be careful with the dates. So December, let's do the mites first. 109.6. So 100. So not quite 110. So that's my point there. And in the exams, if they ask you to draw a graph, they'll be looking at these points and checking them. 103.4 in January. So January 103. So each one of these is 2. So it's not going to be up to 104. It's going to be there. March, so we're skipping February and now we're on to March. 98.2. So that's 98. So there. June, 298.3. So June 298.3, so right up there. And in September 150.9. 150.9. Going to follow our same rules as what we normally do for joining. I'm going to join them up dot to dot with a ruler. We've got even more cause to join these up dot to dot with a ruler now, because this is the mean number. So these have already been meaned, so they're going to be pretty representative. And dot to dot with a ruler. There we go. And it looks like it's a proper approximation over time because we've put all of the months in. I'm going to label this line as mites. So I'm just going to put that there. Some of you, when you drew this, you did it in different colours and all sorts of things. But remember, in the exam, what you're going to have is a black pen and a pencil. And really, you're going to be drawing this in pencil. I've done it in red just to make it stand out. But you draw it in pencil, then if you make mistakes, then you can rub them out. And the best thing to do is just to draw the line and then clearly label it. Sometimes it gets a bit complicated if you draw dotted lines and thick lines and things like that. So just draw the line and label it. Again, the origin is there, but we're not going to put a point down to origin because we haven't got any data to support that. And let's do the columbulands. In December we're going to start off with 163.7. So 163.7. January 60.5. March 23.6. June 58.3. And September 60.1. 60.1. Pretty difficult to put 0.1 on this scale. And again, joining them up dot to dot the best that we can. We're not going to worry that they cross over because we're going to clearly label our lines at the end. Now I'm going to clearly label that. I'm going to copy the correct spelling. No excuse for not spelling it right, because I'm just copying it. There we go. So a nice clear graph. We've got the right scale, we've got the origin labelled, the axis is labelled, units if needed, so there's not actually any units here. The lines are joined with a ruler. We haven't got any extrapolation, and we've labelled the lines. Then there are reasons, where the question is now, suggest reasons for the variation in the numbers for mites and collembolans. Well, this is not really important from the maths point of view, but really both of these live in the soil, but the mites actually predate or eat the collembolans. So the mites increase when the collembolans go down, and when you do populations you'll see kind of predator-prey cycles. So the mites are predators of collembolans. What's our evidence? As mite numbers increase, collembolans fall. So one is eating the other, and that's that one. We now move on to something that you're probably familiar with, saturation of blood with oxygen and hemoglobin and so on. Where's our question? A fetus and a mother, plot the results, similarities of the curves and differences of the curves. So here we go with plotting our results. We have our x-axis and our y-axis. Our x-axis is going to be the independent variable. Our y-axis is going to be our dependent variable. Independent variable, I choose what the values are going to be. Dependent variable, it depends on the experiment. We don't know what it is. That's a good way to remember those. So our independent variable is partial pressure of oxygen, and we're going for values 1 to 11, that's what I'm thinking of, so anything between 1 and 11 on the scale. Does our nice simple scale 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's perfect again, isn't it? Suspiciously so. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to put a figure for the origin there, and up the side values up to 92, so we're looking to go up to 100, and if we went up, let's have a look, just put these lines on to make it a bit clearer. Pretty hard to see some of them. Okay, if we went up in say tens, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, we get to there, looks about halfway. But if we did it in 5, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, that would fit on as well. So we're actually going to go up in 5s here, So 0 and then 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. I'm going to draw the axis lines. I'm going to label these axes, because if I plot the points now, I'll probably forget to do it later. So, we're just going to write this out. So, partial pressure of oxygen kilonewton meters minus 2. So kilonewtons per square meter, strange unit. But I've just copied it out, so it's going to be right. And up here we've got percentage saturation of blood with oxygen. Percentage saturation of blood with oxygen. And I'm just going to plot these points as quickly as I can. So 1.1, let's plot the mother first, 8. So 1.1, 8. 2.5, 18. Pretty tricky to do on this graph paper. 3.2, 27. 3.2, 25, 26, 27. 4.0, 42. 4.0, 41, 42. 4.5, 52. So 4.5, 1, 2, 3, 4, 5, 52. 5.1, 62. So these are pretty tricky to plot. 5.8, 72. So not quite 6, so 5.8, 72. 6.3, 76. So 6.3, 76. 7.2, 82. 7.2, 82. 7.9, 85. So 7.9, 85. 8.5, 87. 8.1, 2, 3, 4, 5, 87. 9.2, 89. 9.2, 89. And 10.5, 91. So 10.5, 1, 2, 3, 4, 5, 91. There we are there. So I'm just going to join these up as best I can. And this graph looks reassuringly sigmoidal or S-shaped, exactly what you'd expect there. We haven't got a point down here, so we're not going to keep this going to the origin. And I'm going to label that with, what did we have? We had mother there, didn't we? Yes, that's mother. And again, we're going to do the same with our theta, so as quick as I can. So we've got the same, helpfully we've got the same starting points for our independent variable, so it's just a case of putting the different numbers on. So 9, 27, 42. So 3.2, 42, 1, 2, 4 is 59. 4.5, 6.8, 68, sorry, 68. 5.1 is 75. Oh, I've done that one wrong. There you go. I have made a mistake. So 5.1 is 75. 6.3 is 85. So 5.8 is 82. Probably because I'm losing the will to live drawing this graph. 6.3 is 85. 7.2 is 88. 8.5 is 91. Oh, we're getting there, we're getting there. 9.2 is 92. And the last point is 92 as well, so 10.5 is 92. So we're going to join those up, ignoring my little faux pas there, which exactly shows why you should use a pencil for these instead of trying to show off by drawing it in a red pen. So you'd be using pencil, you would have rubbed that out. Point up right. 4.5 is 68. 4.5 is 68. Yep. Maybe a little bit higher, yep. And there we go. And we can label this this graph fetus. And the questions were similarities and differences. So similarities here, the fact that these are essentially the same shape. That's what we want to say. They're both, you know, sigmoidal and so on. So both same shape. You know, sigmoidal. And the difference is we're not looking for loads of numbers here, but the point is that the fetus line is higher than the mother's line. But we need to say that using our information from the table there. So we say, the fetus has a higher, and let's just say this, percentage saturation of blood with oxygen. When? All the time. So at all, and then let's say this thing down here, partial pressures of oxygen. And this means that, as you know from your theory, that the fetus blood has a higher affinity for oxygen, so oxygen passes from the mother to the fetus. So fetus's blood has a higher infinity for oxygen, you know, it's to the left. So oxygen passes from the mother to the fetus. I'll attempt to draw this last graph. The video is going to run out at some point. What's the question? Some plant hormones, a series of concentrations, plot the data, come to some conclusions. So here we've got pluses and minuses, and we've got some 10 to the minus, we've got some indices there. So let's start off in the same way though. We've got an x-axis and a y-axis. We've got x and these are our y's. X-axis is our independent variable, which is our independent variable, and the y's are going to be our dependent variable. Here these are indices, but we can plot them in much the same way. We can go, right, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, so 1, 2, 3, 4, 5, 6, 7, 8, loads of room there. So I can probably go one either side just to make it look really neat. These are evenly spaced as well, unlike those months that we had in the previous graphs. These are evenly spaced. I'm just going to put these on here. So I'll actually start off one below because I need a figure at the origin. So 10 to the minus 7, 10 to the minus 6, 10 to the minus 5, and so on. 10 to the minus 1, 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2, which is 100, and so on. And I'm going to draw that line on that axis there. Up here, right, we've got 0 at some point on here, so we need to have a look at, we need to go down to what's our biggest minus number, minus 100, and our biggest plus number is 240. So we're looking at about 340 range, 340. And so if we add these as tens, then what would, so we can get 10, 20, 30, 40, 50, 60, 70, no, it's not going to be enough. We're not going to run out. So we have to do it in 20s. So each one's going to be 20. What's our lowest number that we need? We need minus 100. So I'm going to have minus 100 and then 20, so minus 80, minus 60, minus 40, minus 20. That's going to be my 0. And if that's 100, can we get to 240? Yeah, there's going to be loads of room there. So that's the scale I'm going to use. I'm going to have 0 here, our minus numbers in 20s, and then go up in 20s again. So 20, 40, 60, so yeah, 20, 40, 60, 80, 100, 20, 40, 60, 80, 100, 20, 40, no, just double check it's going to go on there. 140, 160, 180, 200, 220, 240. There we are. And I'm going to draw this line here. Let's label our axes. So this is concentration of auxin in parts per million. Concentration of auxin, I can't spell auxin, ppm. So I've just copied that, and this is percentage increase or decrease. So the scale up here it's going to be percentage increase or decrease in growth. I'm going to put my line for my 0 across here, and there's a couple of different ways of drawing a graph. We could have these numbers here on our labelled on there. Sometimes they get in the way of the points, but that'd be another way of doing it in our label there. I'm just going to leave mine like this now. So we just need to plot our data. So be careful with the pluses and minuses. So 10 to the minus 6, start off with the root plus 5, so 10 to the minus 5 plus 20, 10 to the minus 4 plus 25, so be careful because these are 30 in between, 13, then it goes into minus numbers, minus 25, so minus 20, minus 30, minus 25, minus 60, minus 95, and minus 100, minus 100. Okay, I'll join those up. We don't have a figure at the origin, so I'm just going to join up the points that I have. Go and label my line. So I'm going to label my line as root. Let's plot the shoot data. We have got excellent points, 0 and 0 to start off with. 0, 0, 10 to the minus 4 plus 2. 15. So these are almost on top of each other. So we've got sort of 10 there. Plus 70. $170. 240. 200 and plus 40. And so I now join these up. That's 217, technically that would have a line going across there. Not a brilliant straight line, that. It comes from having a bendy ruler. hope you've got a straighter ruler than me. And there we go, and let's label that line as well as a shoot. And there's our graph, and hopefully we've got some kind of clear trends now. So let's just check we've got everything that we need. Axes, labelled, units, and the scale is even. And we've got at the origin we've got numbers. Plots correctly plotted, hopefully. Lines joined with the ruler, we haven't got any extrapolation, and both lines are labelled. And then we might have some conclusions there. So let's have a look at this shoot. You don't know much about this, but just from what you can see. So at concentrations, low concentrations, not much happens, but above this number here, so 10 to the minus 3, then we get a rapid increase in growth up to whatever that is, the peak, so 10 to the 0 parts per million, and then after that it goes down. So shoot, so big increase in growth, so at concentrations above 10 to the minus 3 parts per million, rapid increase in growth up to 10 to the 0 parts per million, then the percentage increase in growth is less than the percentage increase in growth declines. A horrible thing to say is that. Remember, this is all growing. The shoot is growing, but it's growing slowly, and it's growing really fast, and then it's not growing as fast, but it's still growing. Okay, it's not getting smaller. And the root, so concentrations, growth is increased, got between there and there on the graph, so between 10 to the 6 and just above 10 to the 3, and then where's it increased most? 10 to the 4, and then growth is inhibited, so there's a decrease in growth above 10 to the 3. So increase in growth from 10 to the minus 6 to about 10 to the minus 3 parts per million. Most increase at 10 to the minus 4 parts per million of auxin, and then above 10 to the 3 parts per million of auxin, then there's a decrease in growth. So quite a complicated graph to plot, that's why we're giving it to you, and quite complicated to actually describe it, but it's just really saying what you see and trying to use these scales accurately. Well done.